String theory is the most ambitious attempt to unify all forces in matter into a single framework. At its heart is a simple idea: replace point particles with tiny vibrating strings. A point particle traces a one-dimensional world line. A string traces a two-dimensional world sheet. Different vibration modes of the string correspond to different particles, including the graviton. Gravity emerges naturally. String theory requires 10 dimensions for mathematical consistency. 6 extra dimensions are curled up at the Planck scale into shapes called Calabi-Yau manifolds. The shape of these extra dimensions determines the laws of physics in our 4D universe. Supersymmetry pairs every fermion with a boson superpartner. It stabilizes the extra dimensions and predicts particles at TeV energies. The LHC has not found superpartners yet. There are 5 consistent string theories: Type 1, IA, IIB, SO, 32, and E8x-E8. In the 1990s, M-theory unified them all in 11 dimensions. D-branes opened new possibilities. The string landscape contains an estimated 10 to the power of 500 possible vacua, each with different physical laws. This explains the fine-tuning of our universe but challenges predictability. String theory remains the most mathematically beautiful and promising candidate for quantum gravity, even without experimental confirmation.